So we're getting into graphing polynomial functions, and we just started getting techniques or characteristics of polynomial functions and their graphs. And so we learned how to find the end behaviors of a graph, and it had to do with the leading term. So the leading coefficient was that positive or negative, and was that degree of that polynomial even or odd. And depending on those couple of things depended on what way it went. We saw that even powered polynomials, the degree that the end behaviors shot in the same direction, and odd degree they shot in opposite directions. And then we also started to talk about multiplicity of zeros, and that told us what was going on with the graph. Was it touching the x-axis there, or was it crossing? If it was an odd multiplicity, it crossed, and if it was even, it touched. Okay, and then really quickly at the end of class, we talked about if you had a degree n polynomial, there were n-1 terms. And so recalling all those things, let's say we're looking at a graph and we want to answer some questions about what type of polynomial it could be. So let's give you a graph. And so let's say it's crossing through the x-axis at -1, but as x is going to -infinity, it's shooting downwards. And then it's coming up and it's hitting the y-axis at 1. Coming back down and crossing the x-axis at, or not crossing, just touching at 1 and turning back around. And then at 2, it crosses. Okay, so find a polynomial function that might give be the given graph. Let's go back up here. So identify which of the graphs could be a graph of a polynomial function. So this could be a graph of a polynomial function because it's smooth, so there's no sharp corners, and there's no jumps in the graph. It's continuous. For those that could list the real zeros and state the least degree of the polynomial can have. Okay, so the real zeros. So those are the values where the graph is crossing or touching the x-axis. And so we can see that, and I told you that that was going to be at x equals -1. It's touching at x equals 1. And it's crossing at x equals 2. So since it's crossing at these two values, x equals 1 and x equals 2, we know that the multiplicity is odd. Graph crosses. But remember, when it just touches the graph and it turns around, that tells us that that multiplicity was even. So just by knowing that fact, and if they wanted to know the least degree of the polynomial, from that information right there, well, if it crosses, that means, like I said, it was an odd degree. So let's say odd degree is just 1 multiplicity, right? That's the least. So each of these have a multiplicity of 1, or a factor occurring only once. And then if it's an even, the least number of times that degree could be would be 2. So degree 1 plus degree 1 is 2, plus another 2 degrees, that's 4. So far right now, it looks like that the least degree it could be from zeros is degree 4. We need to make sure that everything else holds true to that fact. So we talked about the end behaviors, right? And again, the degree of that term. Well, the end behaviors are both shooting downwards. And so since they're both shooting downwards, we know that this has to be an even degree, same direction of our end behaviors, even power. So even degree. Since both end behaviors are the same. So that works so far with degree 4. That's even. And then the turning points. So we need to look at how many times does this graph turn around? And so, well, we saw one of them, and that was at that 0, but it also turns around here. So there's 1, 2, and here. So we have 3 turns. So the most number of terms was the degree minus 1. And so if we had a degree 4 and we subtracted 1 from it, that gives us a degree 3. And so that matches that the least degree that it could be would be a degree 4. So most terms a degree n polynomial can have is n minus 1 terms. Okay, so from there, say the least degree of the polynomial can have. And that's what we think. Because everything held true for our degree 4, the least degree polynomial we can have is degree 4. But it also wanted us to find a polynomial function that might have this graph. And there's more than one answer that could be possible. And so let's try to put this together. So finding a polynomial that could have this graph. Let's go back to the zeros, because from those zeros, we know what factors are. So if x equals -1 is a 0, then what would a factor be?
+1.
Yep, so x plus 1. So another way to kind of think of it is if I was to set this equal to 0, I would have to add 1. So x plus 1 is our 0. And we said that this one had a odd multiplicity, and we were only counting it to have 1. So far for our polynomial, we have a factor of x plus 1 in here. So far we have f of x equals something times x plus 1. And then so for x equals 2, it was also odd. So the factor is
X minus 2.
yeah. So x minus 2. And then x equals 1 was also a 0. So let's put back down there x minus 2. And then I think you guys have it. Subtract 1, so x minus 1. But this one was even multiplicity. And so we have to have a even, sorry, it wasn't an even multiplicity. We know it's an even multiplicity because it touched. So we need a even power of this. Okay, but there's also one other bit, a couple of other bit of information on here. We know another point on this graph. Notice that we see here that 0, 1 is a point. So technically, we could have a polynomial that looks like this, but technically we could have any coefficient, any number out here, and we would have the same zeros and the same end behaviors. Actually, the other thing we need to know is that the end behavior shoots down. But I think we'll see this when we solve for this number out here. So this could be any number out here, any constant, and multiply it to this, and we would have the same places that we crossed or touched the x-axis. And since both of our end behaviors shot downwards, that's telling me my leading coefficient has to be negative.
I'm sorry, but why does x minus 2 squared?
Because if a graph just touches, sorry, oh, x minus 1 squared. It's because if a graph ever just touches the x-axis and turns around there, this power of the factor has to be an even power. So,
All right. Oh, sorry. I didn't mean to interrupt.
no. So that makes sense. That it has to be square. It could be a 4th power, 6th power. Okay, cool.
Sorry, trying to give a thumbs up.
Yeah, hi Todd. Okay. So both end behaviors go down, so leading coefficient has to be negative. But I think we're going to see that. I think we'll see that we'll get a negative number when we go back in and we use this fact that we have this point here. So basically we have a point, right? We know when x equals 0, our y value, or f of x, is 1. And so we can go back in there and we can plug in those values in here and figure out what a has to be. And so again, so y is 1, so we're going to put in 1 here. 1 is equal to a, which we're trying to find, all times, well, x is 0, so 0 plus 1, 0 minus 2, and 0 minus 1 squared. So let's simplify. And so we get 1 is equal to a, all times 1 times negative 2. And order of operations, if I square negative 1, that becomes positive 1. It's all multiplication in between. So 1 times negative 2 times 1 is negative 2 times a, so negative 2a. So 1 equals negative 2a. And then let's get a by itself, divide by negative 2, so a is negative 1/2. So we just found a polynomial, f of x. So f of x equals negative 1/2 all times our x plus 1, our x minus 2, and our x minus 1 quantity squared.
Why did we set y equal to 1? Is that just because it's easiest to do math with? Could we have made y any number?
I did y equals 1 because going back and looking at the graph, that was one point that I knew on the graph that was not an intercept or a 0.
Oh, okay.
So from that point, I could plug that information in, and that was just that, in that case, y was 1. So if it had crossed up here at 3 or something, it touched up here, I would have said let x equal 0 and y be 3.
Okay.
Maybe I didn't even know what this point was. Maybe it didn't tell me it was 1, and it just kind of went around and it gave me another point. So maybe like they said this point here was 1/2, 1/2, 1.5 and 0.5. Then I would have to go in there and plug in my x value of 1.5 and my y value of 0.5. So I'm just using the information of knowing an x and a y value so that I could go in here and figure out what this coefficient had to be to give me that point. Okay, so let me, I'm going to pause the video while I get up Desmos. But let's go into Desmos and look at the graph. And Desmos was the graphing calculator that you can use online. Okay, so we just put into Desmos and we typed out that equation we just found, and notice that our graph is similar. It's crossing the x-axis. Oops, actually my graph is a little different. But it was crossing the x-axis here. Ours had a peak here. But it has the same characteristics right here. It's turning around at 1 and crossing here. Okay. So we're going to jump into the next section, which is 5.2. And sometimes it asks you to use graphing calculators to help you. So right now we have the tools where we can figure out where and what's happening at our x-intercepts, or some of them. We'll learn some more a little bit later. But we don't have the tools to figure out what these maximum points are and what this minimum point is without some calculus. And so we're going to have to use the calculator to help us to figure out what those points are. And so if you put in the equation in here and you just hover over where the max and min are, you'll get some points, and we can then just estimate, okay, we have a max here about -0.4, 1.4. We have a min here at, well, 1, 0, and we have a max here at 1.6 and 0.19. So we're going to use this a little bit to help us in 5.2. So let me jump. Okay, so we've already actually talked about some of 5.2 and the zeros of the polynomial, and is it going to cross or touch there depending on the multiplicity. So graph each polynomial function by following the following steps. And I didn't tell you what the following steps are. Okay, so graphing the polynomial. So find the end behaviors of your graph. And that's where we looked at the limit as x went to -infinity of ax to the n, where this was your leading term. And we looked at the limit as x went to +infinity. of the leading term, ax to the n. And I had to deal with, is that coefficient even? Sorry, is that coefficient positive or negative, or is this degree even or odd? They tell you to graph the function using a graphing utility. Oh wait, that was for the graphing utility. Sorry, wrong page. Determine the end behaviors of the graph. Find the x and y intercepts of the graph. Determine the real zeros of the function and their multiplicity. Use this information to determine whether they cross or touch. So find the x-intercepts. Determine if the graph touches or crosses the x-axis. So even multiplicity, it touched. Touches. And odd multiplicity, it crosses. Determine the maximum number of turning points. So remember that was n-1, n being the degree. And use the information from steps 1 through 4 to draw a complete graph of the function to help establish y-axis scale, find additional points on the graph on each side of any x-intercept. So use information, we're going to use this information, let's draw a graph. With the information above. Information found above. And plot a couple extra points on each side of an x-intercept. Okay, so this is without using a graphing calculator. We can kind of get an idea. Is it going to go shoot really high by the values of plugging in a number, or is it just not going to go very high? So let's do this. Okay. So if f of x, let's say, is equal to x minus 2 quantity squared all times x plus 2 all times x plus 4. So let's find the end behaviors of this graph. So what would that degree be? Could you figure out what that degree is, and what would that leading coefficient be without really having to go through and expand that whole thing? I know if I FOILed out x minus 2 times x minus 2, that leading term, that biggest term would be x squared, right? And then if I took that biggest term x squared and I distributed it here, the biggest term is an x cubed. And if I took the x cubed term and I distributed it here, that would be an x to the fourth. And notice that all have a coefficient of 1. And so this end behavior, our leading term is x to the fourth. And so we have to look at the limit as x goes to negative infinity of x to the fourth. So plugging in negative numbers wherever you see x. So plugging in a negative number and raising it to the fourth power, negative times a negative times a negative times a negative is positive. And the limit as x goes to positive infinity of this x to the fourth function is also positive. So we know our end behaviors so far are shooting upwards. So the intercepts. So y-intercept, let x equal 0. So if you go back in here and wherever you see an x, we plug in 0. Well, f of 0 gives us zero minus 2 quantity squared, 0 plus 2, and 0 plus 4. So this gives us negative 2 quantity squared. So this is 4 all times 2 all times 4. So 4 times 2 is 8, times 4 is 32. And the x-intercepts set this equal to 0. So we're looking at let y equal 0. So we get 0 is equal to x minus 2 quantity squared, x plus 2, x plus 4. So the x-intercepts will be, well, it's already factored. This is already nice for us. X equals 2, x minus 2, that, and it touches here because it's an even multiplicity. We have x equals negative 2, and this is going to cross. And we have x equals negative 4, and that's going to cross. Okay. So we know the end behaviors, and why by the end behaviors and knowing if it's crossing or touching, we're going to come down. We know it crosses at negative 4. We could find some points in here. That's what it told us to do. And we'll come back and do that. We know it's going to come back down here somehow and turn around. And again, it's going to cross. We know that we have an x value of 0, y is 32. So I'm just going to say 32 is up here. I'm not sure, you know, is this going to just touch this and turn around here? Or is it going to go up higher? And then I know it comes back down somehow, somewhere around here, right? And it's going to turn back around because this is the one where it just touches. And we know the end behavior has to go this way. So we just need to figure out a couple of values. So let's see. So here, I'm going to give you where Desmos, again, could be really helpful. Let me pull it up. So we can go in and put this equation in here, and then let's just plug in a couple of values for x and let the calculator spit it out for us. Maybe. So here was our function. No, that wasn't our function, was it? Let's go over here. Where'd it go? Okay, so we have, it might be in the wrong one. There's two different ones. I don't know if I hit the right one. So f of x is equal to, it's giving me an error. Let me go back. I swear it was this one though. What was our function? This was x minus 2 quantity squared. And then it was all times x plus 2, x plus 4. So if I looked at f of, we wanted to see what was going on between -2 and -4. So let's look at f of -3. And so if we plugged in -3 in here, our y value is going to be -25. So we know we have a point at -3, -25. Maybe let's see what's happening at -3.5. So let's just put a 0.5 there. -3.5, we have a point about -22.7. So let's look at what's happening. Well, we knew that the y-intercept was at 32. Let's see what's happening at -0.5. That's a little bit above there, 32.8. So it's turning somewhere around. My guess is probably, you know, around there. So -0.75 is 30. .7. And then let's see what's happening at 1. At 1, we have 15. My guess at 0.5, it's gonna, you know, it's coming down from that 0 from 32. I just do 2.5. Is 25. So from those points, I get a little bit better accuracy, and we can do this without, you know, we could be plugging in those numbers for x and figuring out what y is. This is kind of to save us a little bit of time. Okay, so we got pretty good. Actually, let's see. Yeah. Okay, so at -3, that's here, we had like -25. -3.5, Okay, so that's about here. It was negative 22.7. So it's coming down. It's going to turn around here somewhere. It's going to come back up. We saw that it got a little higher than this 32, not much, and then it turned around and came back down. And these are smooth, rounded corners. Okay, so we got a general sketch of what that looked like by the tools we learned from the other section. Any questions on that? So let's look at one that isn't factored. Okay, so graph each polynomial function by following the steps that we were just doing. So let's say now our graph or our function is f of x is equal to about 4x cubed plus 10x squared minus 4x minus 10. Okay, so end behaviors. Well, our leading term is this 4x cubed. So we're looking at the limit as x goes to negative infinity of 4x cubed. So basically it's 4 times numbers that are negative, going to a negative infinity and cubing them. But if you cube a negative number, that's negative, times this positive 4 in front is going to be a negative number. So this is going to go to negative infinity. So it's shooting downwards. It's an odd degree, so it should be going the opposite direction, but let's just show. So as x is going to positive infinity, basically we're taking 4 times some number that's getting huge, positive, and cubing it. Well, positive cubed is positive, times this positive number in front, it's also positive, so this goes to positive infinity. So somehow our end behaviors look like this. So intercepts, the y-intercept. Well, if we look at f of 0, go in here and plug in 0 wherever you see an x, all of those terms are going to be 0. The only thing that we'll be left with is this constant negative 10. Okay, so we know down here somewhere we have a point at 0, negative 10. How are we going to figure out, or how are we going to factor f of x? Any clues or suggestions? So when I look to factor, there's certain things that are helpful. And one of them is looking at how many terms you have. So if I look at this and I notice I have 4 terms in here, then factoring by grouping might be the way we want to go. We could rearrange our groupings if we want or not. I also noticed that all of these coefficients for 10, -4, -10 all have a common factor of 2, which we can also pull out. So let's look at this. We have f of x equals 4x cubed plus 10x squared minus 4x minus 10. So if we group to these two terms together and these two terms together, let's pull out what they have in common. So 4x cubed and a 10x squared. 4 and 10, they both have a 2 in common. And an x squared and an x cubed, they both have a x squared in common. So if we pull out 2x squared from both of these terms, we're left with a 2x plus 5. And then pull out what they have in common with -4x and -10. They both have a -2 in common. So if we pull out a -2 from both of those terms, we're left with a positive 2x and a positive 5, which we wanted the same thing in these parentheses in order for it to be factored, to be able to factor by grouping. So pull out what those parentheses are, 2x plus 5. So if we pull that out of there, you're left with a 2x squared. And if we pull this whole parentheses out of this piece, we're left with a -2. So we want to know, when is 2x plus 5 equal to 0? And when is 2x squared minus 2 equal to 0? So if we subtract 5 divided by 2, we get x is -5/2. We can try to factor this. We could use the quadratic formula. We can use the square root method. Pull out a 2. I get x squared minus 1. X squared minus 1 is a difference of squares. X minus 1, x plus 1. 2 is never 0, but x minus 1 is 0 and x is 1. And x plus 1 is 0 and x is -1. So notice that these factors all occur just once. So those are our x-intercepts. The multiplicity of each one is 1. So we're going to cross the x-axis. At these values. Okay, so we said 1, -1, and -2.5. Okay, so again, we know that of the end behaviors, it's going down. So it's going to come here. It's going to shoot down. We know that it's crossing. We don't know exactly where it's going to turn around, but we can put in our values. It's coming down because it's crossing. Somehow it's touching this. I don't know if it's going down further or if it's going down further and coming back up. And then it's going to be crossing at x equals 1 and shooting upwards. So plotting a couple points in between this -2.5 and -1, and maybe between -1 and 0 and 0 and 1 would give us some ideas of what was happening. What do we say? -2 How about negative 1.5? How about negative 0.5, 0.5? Okay, so let's go in and plot that. Okay, so we went to Desmos. We got that when x was negative 2, y was about 6. Didn't do negative 1.5, but negative 0.5, I get negative 6. And then at negative or positive 0.5, I got negative 9. So this would be a general sketch of what our function would look like, with finding the end behaviors, our intercepts, what was happening at those intercepts, x-intercepts, and then plotting a couple of extra points.
When we factored out 0 equals 2x plus 5, wouldn't that be 2x plus 5 squared, which means there should be a place where it just touches?
No, because we're using, they each have just one factor of 2x plus 5 in common. And so think of it as that you're pulling this whole parentheses out. And if I pull it out of this term, I'm just left with this 2x squared from this piece. And if I pull it out of this, which is only one of them, I'm left with a negative 2 here.
Okay.
That would have been different if this had been a quantity squared. We would have pulled out a factor of a square. And then that would have been that our negative 5/2 or negative 2.5 was touching and not crossing.
Okay. So when we factor by grouping, we don't, if we get the same thing in the two different groups, we don't add those together.
Right, right. So basically, or think of it this way. So if I have I don't know how I want to say that now. Yeah.
Okay.
Or if we have, sorry, that's just went away. But let's say we had maybe an x squared plus x to the 4th. So the most that they have in common in here is just an x squared. And so if I pull out an x squared from there, I'm left with 1. And if I pull an x squared out of there, I'm left with an x squared. So we're just pulling out the most that they have in common. It just happens that what they have in common was in parentheses.
Okay.
So we could pull out the blah and we would be left with just the A there and then plus the C here. So normally we think of it just pulling out like a term, but it's now that we're pulling out this whole expression, which is a fraction. Okay, so that was 5.2. Next, we're going to look at properties of rational functions. So we're kind of going in a different order than I've done in the past, but I don't think that it's bad. But 5.3 also talks about long division of polynomials. And so that was something that's supposed to be a review, but I'm not sure how much of a review it is. So that's something that we'll come back and look at after the break.